Hi everyone, I'm Zoé DARY, a third-year PhD student in cognitive neuroscience in France in Marseille under the supervision of Dr. Christophe Lopez. The part of my PhD work focused on the brain network involved in the bodily self. The bodily self is the experience of having and being a body. And neuroscientific researches define bodily self by several bodily components. For example, self-location is a subjective experience of being localized in a volume of space. Agency is a subjective experience of being at the origin of my actions. Body image is the perception of own body that can be verbalized, for example, size, weight, body shape. And disturbance of these different bodily self-components can be observed in patients with neurological disorders. For example, the illusory perception of being disembodied, called out-of-body experience, can be observed in patients with epilepsy or migraine. Depersonalization is another bodily self-disturbance in which patients have the sensation of being detached from their body, losing control over their body. Several experimental manipulations of the bodily self components have been developed and adapted in neuroimaging techniques. These studies showed a widely distributed network. For example, the regions involved in self-location and first-person perspective are the postcentral gyrus and the temporo-parietal junction, including angular gyrus and supramarginal gyrus. Studies show that sense of ownership involves premotor cortex, and agency is associated with an activation in the premotor cortex and in angular gyrus, and body image with intraparietal sulcus. Another way to study the network involved in the bodily self is through electrical brain stimulation. This technique enables a causal link between an observed behavior and stimulated areas. And there are different types of electrical brain stimulation used in clinical practice. In patients with drug-resistant epilepsy, for example, stereoelectroencephalography, SEEG, consists in insert electrodes into cortical and subcortical areas and stimulated contacts of electrodes to identify the epileptic area. And another technique is electrocorticography, in which a grid is placed on the surface of the cortex and some electrodes are stimulated. And finally, during awake surgery for tumor resection, for example, some stimulation is induced while the patients perform a series of cognitive tasks. And all these techniques can be used to map brain functions. During a cognitive task, clinician stimulates an electrode and records the patient's responses. And our team has recently published a review of the literature which lists all the electrical brain stimulation that have induced a change in one of the components of the bodily self. And we reported 42 studies and 2021 cases of patients with bodily self disturbances. And a density map showed 6 key regions, which are inferior parietal lobule, posterior insula, supplementary motor area, middle cingulate cortex, precuneus, and hippocampus. And the aim of this current study is to identify the brain areas causally involved in the bodily self and to describe the functional connectivity within this network of bodily self. We have conducted a retrospective analysis of 354 patients underwent SEEG for pre-surgical evaluation of drug-resistant epilepsy between 2000 and 2021. we have created a database listing all the stimulation that have produced responses in patients. And this represents more than 500 implanted electrodes and over 19,000 stimulations. We analyzed more than 2,000 responses induced by electrical brain stimulation of the cerebral cortex and subcortical structure, and we focus on patients with bodily self-disturbances. 107 responses were bodily self-disturbance in 68 patients, and body image and self-location were more reported than depersonalization and agency. Most of responses were evoked in the right hemisphere, and body image disturbance were caused by higher intensity of stimulation than depersonalization and agency. And these results suggest that higher current amplitude tend to result a greater number of complex subjective reports. And among these 68 patients with bodily self-disturbances, we focus our analysis only on 37 patients who were implanted with MRI-compatible electrodes. The first step is we co-register pre-implantation MRI and post-implantation CT to reconstruct electrode in each patient. We use the virtual epileptic patient atlas to localize precisely electrode, and finally all responses were normalized to a common brain in MNI space, and we analyzed 55 responses. Bodily self-disturbance were evoked in inferior parietal lobule, postcentral gyrus, and precentral gyrus, in insula, in amygdala, and in hippocampus, in SMA, in anterior and posterior cingulate cortex, and in precuneus. The next step is to describe the functional connectivity in the bodily self network. And to do this, we analyze SEEG signals or records, and we compare the connectivity post-stimulation with the one pre-stimulation period. And we want to identify changes in functional connectivity between different regions during patient reports of the sensations. So now I'm taking an example to explain you the methods. So here there are 4 signals. And to compare signal activity before and after stimulation, we perform a nonlinear regression called H2. This is a non-parametric analysis. And we compare whole value of H2 post-stimulation in electrode A with a whole value of H2 in pre-stimulation in electrode A. And we obtain, after statistical test, a Z value which represents the strength nodes, that is the potential changes in A. It's the sum of link starting to nodes. We analyze the tendency of some regions to increase or decrease their connectivity. And we show that the connectivity decrease in supramarginal gyrus, in anterior middle temporal gyrus, and in anterior inferior temporal gyrus, and while the other areas tend to increase their connectivity, such as anterior and middle cingulate cortex. Our study provides causal evidence of the regions involved in the bodily self. Our studies confirm the regions previously showed with MRI, temporo-parietal junction, posterior superior temporal gyrus, premotor cortex, and somatosensory areas. But We show the involvement of other median regions such as the hippocampal complex, the precuneus, the SMA, and the posterior cingulate cortex. I would like to thank all my partners who are helping me to carry out this study. Thank you for your attention.